Um, Hello everyone, this is Shammi, and welcome to week 3 of this course of law of spaces and partial differential equations. Um, I welcome you all. I am a research scholar at the Department of Mathematics of IIT Delhi, and in this week, in the video lectures, we have studied about the convolution of functions, and then that like we studied that in the that you have studied in the week 2, and then we generalized that particular thing to the convolution of distributions, and after that we studied some properties, that's the properties which can be lifted to from functions to the distributions, and after that there's a Fourier transform of distributions also defined in the same spirit as the Fourier series of functions can be defined. So we need the L1 restriction for a Fourier series to be Fourier transform to be defined of a function. So likewise, we have some same restriction that we need to have Fourier series to be defined for distribution functions. So temper distribution functions, temper distribution of those classes will like we cannot define the distribution for all class of distribution. So we have to restrict our class, and that particular class is known as the tempered distribution class. And after that, we see some applications in solving these uh, partial differential equations involving distribution with the help of this Fourier transforms. So today we will do questions based on these topics only. So um, we will see that first of all we'll see some nice examples of convolution of functions. So first of all, so let me write the question number 1, which is very nice. Application of convolution, and we will see that this particular convolution thing actually satisfy a very nice property known as the semigroup property. And many kernels actually or potentials satisfy particular property, and they are very helpful in this solving different partial differential equation theories. So let me write the question and we'll see that what is this semi property and how is this here useful. So for A in R, let F and G be the functions defined by Fx is defined by Hx e raised to power of Ax x raised to power of alpha minus 1 gamma alpha Gx is equal to Hx e raised to power of Ax x raised to power of beta minus 1 gamma beta. Where what are these alpha and beta? Alpha and beta are some positive constants. And Hx is the Heaviside function. So what do we now have? If this denotes the Heaviside function, then the convolution of Hx Eax x alpha minus 1 gamma alpha Hx Eax x alpha plus beta minus 1. So ultimately we have some sort of function defined terms of alpha, And when I convoluted beta, so the result is alpha plus beta in terms of alpha plus beta. This actually convolution is in terms of distribution only, because these functions are not actually integrable. But and let us do it formally for like in distribution sense. So Heaviside function, as we know, is given by this thing that it is when x is non-negative and zero otherwise. So if I take fx to be hx, eax, x gamma alpha, and gx is hx, eax, x gamma beta. So alpha minus 1, and then there's beta minus 1. And then we know that fx is 0 and gx is also 0 for all x less than equal to 0. So then, so basically, we have both this function to be to be 0 when n x is less than equal to 0. So this will imply that f star g for x less than 0 has to be 0 only, because for all x less than equal to 0. So this is like from the definition only. Now for x positive, f star g x is nothing but, so it's a Heaviside function. It's like uh, 0 to infinity. Um, ft g x minus e dt. So let us put the value of these functions. This is 0 to infinity. What is ft? Ft is up to ht e at t is for alpha minus 1 whole divided by gamma alpha. And finally, g of x minus t can be written as g was again h x minus t e alpha x minus t x minus t to the power of alpha minus 1, and then finally we have gamma and beta. So here also we have a beta dt. So now this thing is 1 here in ht is 1 here in 0 to infinity. So already in the range to be the domain to be domain of integration to be 0 to infinity as we basically have heaviside function to be 0 whenever t is less than 0. This is nothing but 0 to and now hx x minus t is non-negative only when my t is from 0 to x only. So this integration is 0 to x e a t t raised power of alpha minus 1 gamma alpha. In fact, gamma beta is also there. And then e was actually a only. E ax e minus at x minus t raised power of beta minus 1. And that's all we have. So it's like 1 upon gamma alpha gamma beta. And moreover, we have this e ax to be constant 0 to x e alpha minus 1 x minus t raised to power of beta minus 1. So that's all we have. So this seems like to be gamma integral. So we need to change a variable. So we put t by x to be s. So then this integral e ax gamma alpha gamma beta. Already we have x's to be non-negative, so I can divide by x. This is 0 to 1. X is power of alpha minus 1. E is power of alpha minus 1. X is power beta minus 1. And this will be 1 minus s. So this was s 1 minus s beta minus 1 ds. And then there's a x as well. So it's actually x dx. This is nothing but e raised power of ax. X is power of alpha plus beta minus 1 gamma alpha gamma beta 0 to 1 s to power alpha minus 1 1 minus s beta minus 1 ds. So this is nothing but if sorry, this is nothing but the beta integral of first kind. So e ax x is for alpha plus beta minus 1 gamma alpha gamma beta, and this is nothing but beta of alpha comma. This is basically a beta function, and this actually we write more away. This beta at alpha and beta. And actually, what do we know about this beta alpha beta? This is nothing but gamma alpha, gamma beta, gamma of alpha plus beta, ax, x alpha beta minus 1, gamma alpha plus beta. So this is actually what we wanted, and that's the convolution we have. So this is the result. So this is the computations. So you can see that here, even though the fx and gx are basically are not locally integrable functions. still we are in a position to define this uh, convolution here. So that is not in general true. Like if we take just constant function 1 and 1 only, then its convolution is not defined. But in some cases, we do have the existence of the convolution. So this is the remark basically we have here. So even though f and f for g, neither f nor g belongs to L1 of R, still we are able to define f convolution g. So it's one of the examples where we have this phenomena that even though they are not integrable, still the convolution can be defined. Okay, so moving on. Next, what we would like to see, we would like to see a sort of same type of phenomena that we know that when we define the convolution of distribution, so we uh, need, like if we are defining the convolution of n distributions, like recursively, we need at least n minus one have a compact support. Otherwise, in general, the convolution may not be well defined. So that particular thing we would like to see that we need this compact support to first to have this particular well-definedness of our convolution thing, and then as well as at the same time we what we extract we get associativity when we have this compact supports of our distribution of at least n minus one distributions. And and this is like the associativity is at least something we want because we have to uh, have a uh, multiple convolution of distributions. So to see one example, basically we have next question highlighting this a particular fact that if the if n minus one distribution doesn't have the compact support, but how things uh, can go wrong. So the second question is we have two distributions which doesn't have compact distributions, and we are convolving three distributions, and we see how things go wrong. So um, let equal to 1 s equal distribution generated by 1 has to be the derivative of the diagonal distribution, and h to be actually nothing but the distribution generated by Heaviside function. Heaviside function. So what we will see, show that um, T star is star h and T star S star h is is defined, are defined, but not equal. So even though they are defined, but they're not equal. So we are losing associativity here. So how to deal with this type of question? So basically, we will evaluate these convolutions directly, and we actually will see that they are not answered to be equal. And we will use some of the facts that uh, since this Dirac delta, the derivative of this has actually a compact support. This will help us using the facts which we have developed, which we have seen in developed in the lectures. Okay, so let's without further ado, let's try to compute this problem. So one of the facts which we would like to use is that we know that the distribution derivative of this heaviside function, so dh by dx is nothing but delta. So this is in sense of distributions. So this is in terms of distributions. We know that the derivative is this. So let us compute first thing, the t star s star h. What exactly is this one? Convolve with delta dash, all convolve with beside function only. So since delta dash has a compact support, so one star delta dash is well defined. And since this has a complex support, these basically can commute. This is delta dash 1 star h. And what is delta dash star 1? So this is actually it's the zero distribution. And how do we see this? We see is like 0 star h. Since so how do we go about that? We see that the delta dash star 1 is nothing but the d of derivative of delta convolution with 1. And since that is the case, so we can transfer the derivative of the constant function 1. So this will be generated by 1. So this is delta star d of 1. But now since derivative of 1 is nothing but 0, so delta star 0 is and turns out to be 0 only. Or also we can use the fact that delta star 1 is 1 only. So then that will also give us the same thing. But this actually will give us this is only 0 distribution generated by 0 only. But if we try to evaluate the t star of S star H, this is nothing but T is nothing but 1 convolve with S was delta dash star H. Now what is this? This is 1 star H dash. How we are again getting? We're going to do the same idea. Delta dash star H is nothing but D of delta star H. But what is delta star H? This is nothing but H only. And this is nothing but H dash. So any convolution with drag delta gives us the same function which we are convolving with. So that's another type we are using here. And we are again using the fact that H dash is nothing but Dirac delta, and 1 star delta is nothing but 1 only. So again, we have the convolution to be exist for both of the cases. In one case, we're getting the distribution to be generated by zero function, and in another, we're getting to be the distribution generated by the one function, the identity function, the constant one function. And clearly, both are not equal. T star h is not equal to T star S star h. So even though they both exist, they are not equal. So both not equal. They are both not equal, but what we have the existence of these things. Both not equal, but exists. Okay, so that is another thing to keep in mind that whenever we are convolving, so at least in -1 distributions should have compact support when there's a convolution between n distributions. So next another sort of same thing like the extreme cases which we are talking about. So next thing which we'll now talk about is that if we have some arbitrary distributions T and S, so again it is not may not be the case that T's convolution with S is well defined, but we have a situation that the derivative of one distribution convolution with another S, or the T, let's say the two distribution to be T or S only. So T star, T convolution S may not be defined, but there is a scenario that the T dash convolution S or T convolution S dash may be defined. So that might happen. So it's not the case that if T convolution S is not defined, that doesn't imply that the T dash convolution S or T convolution S dash is well defined. So we do have cases like this. So to see this, we will see we have another question based on this. So for question 3. So what do I have to show? I have to show that that even though at T and S are some distributions, so that T convolution S may not is not well defined, but is not defined, but the derivative convolution from the same distribution is defined. So show that there is T and S distributions with T convolution S is not defined, but uh, T dash convolution S or T convolution S dash may be defined. So to prove this, or to show this, the generally to have basically prove this type of things, generally one rule of thumb, we generally start with functions which are like very basic. We have the Heaviside function, the identity function, or the drag delta function, or derivative of drag delta functions. These are the basic tools when we try to see things, when try to go wrong or something, have to see the cases which are outlier cases. So these functions are really helpful when we are considering this type of stuff. So let me write. So let us see this. So I will take my t to be Heaviside function, is to be the function generated by one identity function, and it is clear that t convolution S is not defined, because if you see that t convolution S, if convolve with phi, will turns out will actually it's not well defined, because phi convolute with one will give you integration of phi, and then that integration of phi over the Heaviside function over 0 to infinity is not finite. But t dash convolution is, what is this? This is, what is t dash? T dash is the Heaviside function. So derivative, as we have seen just now, nothing delta convolution with identity function, and this is, I know any function convolute with delta is the function itself. And t convolution S dash is nothing but Heaviside function convolute with the derivative of one function is actually Heaviside convolute with 0, and that is actually turns out to be 0 only. So clearly t dash convolute with S is not equal to t convolute with S dash. And actually this is happening because both t and S doesn't have compact support, or at least one of them also doesn't have compact support. So we have an issue here. So one more thing that which you would like to see, that if actually the remark here, you have a remark that the derivative of t convolution S is equal to derivative of t convolution with, oh, let me write this in the sense, t dash convolute with S, t convolute with S dash. This equality may not hold if we consider derivative in pointwise sense. So if we take t to be the Heaviside function, and f is to be some distribution generated by f, which is in basically dr, so it's some CC infinity function with compact support. It's the compact supportly function. Then if I take t of t star s, d of h star f, and that is dh star f, if one equality is there. and the derivative of Heaviside function is Dirac delta, so delta star f, and there's nothing but f only from the theory, but if I consider derivative of h, so ultimately this h is a Heaviside function and has a pointwise derivative except at 0. In the usual pointwise sense, then what do we know that dh of dx at x is 0 for all x non-zero. Then this dh of dx convolve with f is nothing but integration of r ft dh by dx x minus t dt. But I know the dh by dt is point was 0 almost everywhere except at 0. So this will actually give us 0 only. But what this implies actually implies that if we take du by dx of h star f is not equal to dh by dx star f. So we don't have equality here, then we have to be very careful when we are considering the derivative in point functions. So we are this equality will again may not also. We have to consider derivative in distribution sense only. So let's continue our discussion. Next, another thing we will see in a nice example of convolution of distributions. Basically, that involves drag delta distribution. But we see how nicely it happens. It had basically convolve with the functions, and the functions we are considering are actually also very nice. So let me write my question. That question number 4. What it says, if I let pizza equal to z is power of m plus a1 into z is power of m minus 1 plus am minus 1 xi plus am equal to product of I1 to m. So there are two forms in which one can write polynomial. Xi minus lambda x. This is be a polynomial of degree m with real roots lambda 1, lambda 2, lambda m, such that lambda is may or may not be distinct numbers, and distinct numbers, and we are considering the corresponding differential operator to be given as differential operator PD be defined by dm by dxm plus a1 d of m minus 1 d of x m minus 1 to am, or we can have another form d by dx minus lambda 1 and d by dx into minus lambda m mth root with d is given by d by dx. Then we have to show that the PD of delta is nothing but d delta minus dx minus lambda 1 delta convolved with d delta of dx minus lambda 2 delta convolved with, again, this d delta dash and delta have a compact support. So this convolution is well defined because all the functions have a distributions have a compact support. So we can, like, we have associativity, so there is no need to put brackets here. D delta by dx minus lambda m delta. What is this? D delta is the Dirac distribution. So let us solve this. So the main idea we'll use is that that convolution any delta with the distribution is the distribution itself. So that's a key fact we use with this. So PD delta, if I consider, is nothing but PD delta convolution delta is equal to d by dx minus lambda d by dx minus lambda 2 d by dx minus lambda. Delta is convolved with delta. So this can be written as basically d by dx minus lambda 1. This operator actually applied on d by dx minus lambda 2 d by dx minus lambda 3 up to d by dx minus lambda n delta convolved with delta. So basically we're taking out the derivative from the property. We know that since we have a compact distribution, so I can take the derivative out of convolution, and then what can I do? I can throw the derivative to the second operator. This is nothing but d by dx minus lambda 2 to d by dx of minus lambda m delta convolved with d by dx minus lambda 1 delta 1. So now I guess the idea of now is clear to how to prove this. This is only delta, sorry. So next what we will do, we will write this as d by dx minus lambda 2 d by dx minus lambda m delta convolved with d by dx minus lambda. So basically you can write this as d delta by dx minus lambda 1 delta, and this again convolve with delta. Again, since all have a the compact support, so I can write without writing bracket because we have associativity here. And then again, this can be written as with the same steps. With same steps, this is nothing but d by dx minus lambda 3 to d by dx of minus lambda m delta convolve with d delta by dx minus lambda 1 delta, then convolve with d delta minus dx minus lambda 2 delta. Proceeding the same way. Same manner, our assertion is proved. So that was just using the facts and then solving the questions. So now we will have some questions based on the Fourier transformation. Some Fourier transformation questions, and we will see some not so trivial Fourier transformation questions, and basically Fourier transformation the distributions. And again, this Fourier transformation on the distribution actually is quite helpful because it helps in solving our PDs involving distribution very. It makes solving very easier. So to have it's good to have a very good knowledge of how Fourier transformation acts with the distribution, how Fourier transformation of different distributions can be calculated. It is very helpful in solving PDs. So our next question the based on the basically Fourier transform distributions only. So for real number A, which is positive, consider the following series. In S dash R, this is the temper distribution. So the temper distribution, summation in 0 to infinity, A raised to power of n delta n, where delta n is Dirac delta. Concentrated at n, and then show that this series converges in S dash R for a less than non-negative and diverges for a greater than 1. So we have to show that this particular series converges whenever my a is less than equal to 1 and diverges when a is greater than 1. So this more or less behaves like the power series, behaves geometric series, but except for the case when a is equal to 1. So it's a bit different case there. So to prove this, what we basically do, we will use the basic facts of our scores functions, because any phi we are applying is actually will come from a scores space only. Yeah, phi belong to the score space. Then basically we have a from the actual definition of scores functions. In fact, what we can say that for any that for all phi in score space they exist in M positive such that for all k and L in natural numbers union 0 mod of xk into Lth derivative of phi at x, the whole thing is less than equal to M for all x in R. So this is a uniform bound we have here. In particular, we have in particular we have for all k in n union 0 mod of xk by x to be less than equal to M for all x in R. So again, the uniform bound, the eliminatory bound we are taking. And what this basically implies, this implies that mod of phi x is less than equal to M times x raised to the power of k for all x belongs to R. Moreover, we can choose M such that the mod of phi 0 is less than equal to M, because here we have actually I cannot take x to be 0 here, but since I know phi 0 is a number only, so I can take this bound only. I can choose one particular M, whether this particular thing. Thus, what this basically implies, an delta n of phi this particular thing, the modulus of this thing is nothing but an phi n, right? And this particular thing is actually less than equal to some m times a raised to the power of n, and this is n raised to the power of minus k for all k in n. Then summation n 0 to capital N an delta n phi, this is less than equal to delta at phi, the modulus of this, plus summation n1 to n. Since a is positive, I can a's power n is also positive, and this is nothing but phi at n, so mod of phi at n, and this is less than equal to m plus summation n1 to n an m, and this 1 upon n raised to the power of k. That holds for all k in n and for all n in n. In particular, again, we can take k equal to 2. So again, one thing we cannot here, this is actually, this m is dependent upon n, depend on k as well as phi we are taking, but since we're fixing phi and now we're fixing k as well, so this m is a constant, fixed constant. So if a is positive and less than equal to 1, then this summation k from 0 to n a n delta n phi less than equal to m 1 plus summation n 1 to infinity, and I can raise the erase, I can bound the erase of n by 1 only. So this is n square, and this thing I know is finite only, and this holds for all a less than equal to 1 and for all phi sparse distribution. Thus, this implies summation n 0 to infinity a raised to the power of n delta n converges in as this R. For all a in 0 to 1. So ultimately, as we also know that this we when we talk about convergence H dash R, this is nothing but the weak star convergence we are talking about. So I have to check at individual point phi only. So that actually gives the convergence for the case whenever my A is less than or equal to 1. So next you will see that this series doesn't converges in F dash R in the space of tempered distributions whenever my A is actually greater than 1. So consider the case A greater than 1. So since A is greater than 1, there exists B in real number such that B is in between 1 and A. And with that, with this B, what we will basically do, we will construct one phi. We consider, or basically we can construct and we can construct a phi in square space such that phi x is nothing but of the form b raised to the power of minus x or x positive. So it's like the e raised to the power minus x kind of thing. So it's the same thing, but instead of having e, we have some b. So now what we will do, we will try to evaluate our series on this phi. Then summation and 0 to n phi n will be nothing but phi at 0 the summation n 1 to n a raised to the power of n phi n, and then phi 0 I know is nothing but 1 only. And what is phi n? Phi n is b raised to the power of minus n. This is n 1 to n a by b whole raised to the power of n. But what do we know? That b is less than a. So that means a by b is strictly greater than 1, which implies what? The right hand side tends to infinity as n tends to infinity, n 0 to n, a n phi n tends to infinity as n tends to infinity. And since this is not finite, thus the series summation n 0 to infinity a n delta n diverges in s dash r for a greater than equal to 1. So it's again basically the idea that we are using here, that since a raised to n is there, we have to come up with something so that total series turns out to be infinite. So the basic function we took was motivated from that idea only. So next we have a little bit generalization of our previous series. So now let us consider the generalized version of previous series and see how when do we have the convergence. So again, for real number A positive, consider the series in S dash R. The series is nothing but summation and from minus infinity to infinity, it is power of n delta n. Show that the series converges and S dash R only for A equal to 1. Okay, so we have to see the convergence of this particular series. So now this, whenever this summation varies over integers, the definition of convergence series is given by this form, that the summation n from minus infinity to infinity, A n delta n will be convergent in S dash R if and only if both summation n from minus infinity to minus 1, A n delta n, and summation n0 to infinity, A n delta n, convergent S dash R. But we already saw the conversion of the form, the later series, but summation n0 to infinity, A n delta n is convergent only for A less than equal to 1. Moreover, this summation n minus infinity to minus 1 A n delta n is nothing but summation m1 to infinity 1 by a raised power of m and delta minus m. So this behaves like and this behaves similarly as the former series, as the other series. So this will imply this thing converges only for 1 by a being less than equal to 1. But if we combine both, we get that a has to be equal to 1 only for convergence. Okay, so that's all for this English version. Next, what do we have here? We have something actually convergence. We will see one particular example where we see that when we have divergence of a particular series, let a get equal to e raised power of k square, then check whether the series summation k from 0 to infinity a k delta k converges or not. So we know that to prove this, we know that this cos functions have only a polynomial bound, like something we can construct a smooth function, which is actually which has basically an exponential growth, but not a Gaussian growth. This case could gives us a Gaussian growth. So we can construct phi from this cos distribution such that the mod of phi x is actually nothing but equal to e raised power of x only, x e raised power of minus x actually for mod x greater than equal to 1. So like we have this, we can take e raised minus x and multiply with some smooth function, some SR function which has uh, basically have a smoothing effect in a neighborhood of minus 1 to 1. So then the summation k 1 0 to n a k delta k phi is nothing but summation k from 0 to n. A k is nothing but e k square and phi k is nothing but e raised to the power of minus k. And I know this actually tends to infinity as n tends to infinity. So we have a contradiction. So we don't have a contradiction. We don't have this series to be convergent. So the series diverges. In fact, we can take for a more easier version, you can take just phi x to be e raised to the power minus x square only. In fact, like if you don't like this construction, we can take phi x equal to e minus x square, and that will actually give me this finite 1, 1, 1, 1, 1, and that is not convergent. So with this, we see that there are actually series which are actually not convergent in this space of temper distributions. What you'd like to see is it's something like if a temper distribution. So if it's homogeneous, so we define something homogeneous temper distribution, and what we will see that if I take the Fourier transformation, then that Fourier transformation of that particular homogeneous distribution is again turns out to be homogeneous. So this is the last question, so which we are going to discuss. Let T belongs to be a temper distribution, be a homogeneous temper distribution of degree D belonging to R. So what do we mean by that? Um, that for all lambda positive, if I take T of phi lambda, it turns out to be lambda is for minus n plus T of T phi, where phi lambda x is phi of lambda x for all x in Rn. So what's the theorem say? What the then questions to then show that the Fourier transform which again is in this temper distribution is a homogeneous tempered distribution of degree minus n minus t. So let us try to prove this. So I have to consider t dash of phi lambda, and let us try to see that, but actually we get. So by definition of Fourier transformation, this is nothing but the Fourier transformation of phi lambda evaluated at t. So let us consider. So what is phi lambda at xi? So this is what at Rn 1 upon 2 pi raised to the power of n by 2 phi lambda x is for minus iota and then x dot xi dx. So this is the dot product we have here. 2 pi n by 2 Rn phi lambda x e minus iota x dot psi dx. So now what we do, we use a change of variable. So y equal to lambda x and dy will be lambda raised to power of lambda n dx. This is nothing but 1 upon 2 pi raised to power of n by 2. I get the integration is over Rn only. Pi y e minus iota y dot xi by lambda and this is nothing but lambda raised to power of n dy. So this is nothing but 1 upon lambda raised to power of n, and this is the Fourier of phi at xi by lambda. And this is nothing but can be written as 1 upon lambda raised to power of n, the dilation by 1 by lambda of phi at psi. So ultimately, the T of phi lambda hat is nothing but 1 upon lambda raised to power of n, T of since T is linear, in dilation by 1 by lambda phi at psi, this. And then we know that this dilation is something this is the same sort of thing we are doing, but I know that T is homogeneous of degree D. This will be lambda raised to power of what do we have here? Minus of n plus t, T of phi at psi, and this is what we have here. We have here actually lambda into minus n plus t, t hat of phi only, oh, so it's going to be one mistake here. This is 1 by lambda raised to power of minus n minus t. What this basically give us? This gives us lambda raised to power of d only, t of phi hat, and this can be written as lambda of minus n minus t, t hat. So this gives t hat is actually homogeneous of degree minus n minus t. And this proves our claim. So it was just manipulations. And with this, I end my today's session. Thank you.